Alright guys, we're in Chapter 10, Section 3. And so now we're looking at a hypothesis test for means. Again, we're going to be using the p-value approach to make a conclusion on this. So here's a question number 7 from Section 3. It says, since we have a small sample size, we must verify that it's normally distributed. So we can use the hypothesis techniques we're using, using the t distribution, which we'll be using this one since it's a small sample size. When we verify, we just need to make sure that it's within this probability plot, normal probability plot, or within these values, and that there's no outliers. Since that's the case, we're going to say, yes, the conditions are satisfied. And so now that the conditions are satisfied, we can make our conclusions and determine the hypothesis and all this good stuff. So up here it says that the time in order placed to time in received is 85.7 seconds. That's what is known at the fast food restaurant place. It's 85.7 seconds. So my null hypothesis is that the mean time, it's not a proportion, it's not a standard deviation, it's a mean, is equal to 85.7. Now my alternative is always going to be the same parameter, so population mean, and now we have to look at the wording to see if we think it's greater than, less than, not equal to. So a manager devises a new drive-through system that he believes will decrease wait time. So we want to see if it's less than, it's a decrease, and that'll give us our appropriate hypothesis. And so now, this one's using the test statistic, so that's good. So I can show you how to find a test statistic. To find the test statistic, I'm going to take my data, and I'm going to open it up in StatCrunch. And I'm going to do basically the same thing that we did for proportions, but now I'm doing it for means, so we're either going to use the normal stats, the z-stats, or the t-stats. Since we're not given a population standard deviation, we're going to be going with our t-stats. This is one we'll be using, I think, almost all of the time. And it's one sample, and I have data. Like we have the data here in our variable 1. So it's not a summary of the data. I'm going to do my hypothesis test, exactly what we said a second ago. The 85.7. And we said it would be less than, because we think our new system is going to be awesome and it's going to be better, and so it'll be less than. And so when I do compute, it finds my p-value. That's what we said with proportions. If the p is low, the null gotta go, or the ho gotta go, however you want to say it. All depends on what our alpha is. Our alpha in here is 0.1, right? There it is right there, 0.1, so 0.10. So our p-value is less than 0.10, so I already know I'm going to reject the null hypothesis. But they want to use it with the classical approach, which is finding the critical values in the test statistic. Here is your test statistic right there, the negative 1.51 to 2 decimal places. So negative 1.51, that is our test statistic. And now the p-value they want us to find, which is awesome, 0.0822. 0.0822. 3 decimal places. There we go. And then now we have to make our conclusion. Since we know that we're rejecting, in that other video I sent out with the wording for Chapter 10 and 11, we are rejecting, so I'm looking for sufficient, right? So it's not going to do the not sufficient, we're going to be looking at sufficients. The p-value is less than the level of significance, so there is sufficient evidence to conclude that the new system is effective. That means it's less than the 85.7, so that sounds good. So there's sufficient to conclude that the new system is effective. Oh, it's not greater than, it's less than. And so we should totally be doing an A for this one. All right, so remember, if we're rejecting, we're looking at sufficient. If we fail to reject, it's a not sufficient. So that's how we do this one. Now, I want to look at this test statistic because sometimes it wants you to find the critical values, how we would use this test statistic. We're just using the p-value approach, which is saying p is less than my alpha of 0.01 or 0.10, right? So 0.10. So that's the way that I like to use it. In a lot of statistical journals or research, you'll see the p-value given. And so if the p-value is less than whatever alpha you're using, that's when you would reject the null and say that this new thing that we're doing is better and great and all that other stuff. But using the classical approach, using the test statistic, we would be comparing this number to a t-value. So I'm just going to bring up StatCrunch and show you how to find that t-value. If you go to your calculators and your t-calculator, my degrees of freedom on this one would be based off how many data points I had, which I believe on this one, how many data points do we have? 10. So our degrees of freedom is n minus 1, so we're looking at 9. And we wanted to find the test statistic when it was less than, right? So we're looking at a 1 tail, and I had 10% in a tail. And so I have negative 1.38. So that's right there, negative 1.38. We had a negative 1.51. It's over here, right? It's in the shaded region, which means it's in the critical region. So that's why we know that we would reject if we were doing it the classical approach, because it's in the shaded region. So I have a test statistic of negative 1.51. Here's my cutoff for the 10%, so less than, right, because it was a decrease. That cutoff for there is negative 1.38, and that gives me my 10% to the left. So we got something that had a test statistic of negative 1.51, and the p-value for that was the 0.082, so that's 8% to the left. Since my p-value is less than the 10% that they gave us for the level of significance, we would also reject. So both of the test statistic and the p-value say reject the null hypothesis. So that would be the other way to get this answer, the classical approach. I'd be fine with tests, the final that you're taking, just to be looking at the p-value. So I'll try to make sure on your 10 and 11 test that I'm predominantly looking at the p-value for you to make your conclusions.